it out there now? All right, I'll have to take a look.
Okay.
This is gonna take some calculation.
Shall we get kind of started? I think we'll still have some, we may have a couple more folks coming in. Hi, everybody, you know, whoa. There's a cosmic Hi, everybody, welcome to the March Devil's Gate program. Before we get started, two things. Carolyn's been passing out flyers for the Rotary Club to bet on when the barrel's going to fall into the lagoon. Sounds like it's about the same reward as the poop in the, the betting on poop. And I did really well on, I won second place in the borough poop.
You're the poop queen.
What?
You're the poop queen.
Yeah, well, hey, there are many titles. Also want to remind you that if you remember, we've got the little bucket in back where we collect funds to give to the community center for the use of this building, which is such a helpful thing. And next month, the program is going to be Greg Jarvis.
Get your ass in gear.
Get your ass in gear, yeah. It's a program on the summer sport burro racing. And then May is going to be John Sprunger talking about mushrooms. And I will tell you that I love the idea of learning about mushrooms, and I won't go out and pick them because I'm very absent-minded and it's not a good sport for absent-minded.
It's a real minimal.
But I want to start by introducing Dr. Steve Iona here and thanking him for coming up from the University of Denver to talk to us about cosmic rays. This was sort of a fun roundabout as we figured out this program, and thank Michael Stavey for coming into my office one day and saying, this book says, he's reading it, and this gentleman had to stop at the Cosmic Ray Conference in Idaho Springs, and I was like, what? And then he continued to go out and research and find the plaque that is up at Echo Lake Lodge, designating it as a site of National Historic. And of course you say National Historic up here and we're like, well, we've got to know about it. So then I did wander around sort of going, hi, how are you? Do you know anybody in physics? And fortunately, Rex Rideout was able to come up with a contact, and he's the one who put us in touch with Dr. Iona from the University of Denver. And I really am looking forward to this. We study buildings and people when we do our local history, but we don't do as much industry and science, and we need to. And so I'm really pleased to know that this will be our first physics lecture. We've had two botanists. We had Dr. Weber from University of Colorado, who came up very early on in our lecture series. And then if you remember last year, we had Amy Schneider from Denver Botanic Gardens, who came up and spoke about Alice Eastwood and Alfred Russel Wallace wandering around the sides of Grays and Torreys. We've had Nick do a program on the Energy Museum, so did Dennis Seidel. And we had Greg do geology, but we never had physics. So, Dr. Iona,
well, thank you. Yes.
So much.
Okay. It's great to be sandwiched between poop and asses to have a little physics today. So let me do a little introduction of myself.
Yes.
I am not a cosmic ray physicist. But I am a teaching professor at the University of Denver. I taught high school for a long time, and my father was a cosmic ray physicist here in Echo Lake, Mount Evans, and some other locations. And so as I grew up, well, sure, I'll go with Dad. We'll go up to these places. So my background is from a different perspective, looking up as I grew up, and It also means that I have inherited all of the detritus that went with those. And so I have a lot of that stuff over here that you can take a look at a little bit later on. So I will talk about science. I will talk about people. I will talk about places. And I'm going to start, though, with how do we know that invisible particles exist? And how do we measure invisible particles? And why should we care about invisible particles? Let's see, I bet I can just do this as a shadow. Almost.
I could hold it out.
We'll make it work. Oh, now it's beautiful. This is great. So this is the same thing as one of those, only that's from the 1800s. This is from the 1900s. It's called an electrometer. And what I'm going to do
We're easily entertained up here.
I was counting on that. So what I'm doing is wiping invisible particles off my hair onto this electrometer, and you can see that there's a movable little part that's moving. That's because not only did I put invisible particles on there, I put charged invisible particles on there. And so down the middle, that piece of metal has a charge, and the little piece that can move also has a charge, the same charge, and so they repel one another. And the more charges that I put on there, the more charges that I put on there. What kind of weather do you have up here? That's all bad. Yeah, the battery's low. So the more charges that I put on, the wider the distribution. That's how they figured out that there were charged particles that came from outer space. They charged up the electroscope, and they just waited. And all by itself, it lost charge. And as it loses charge, this little pointer just moves down. And so there were charges that came from outer space, hit this piece that's connected to the metal pieces down below, and gradually it lost charge. There were some invisible particles. They're on your hair as well. And they found out that there was a difference in the number of charged particles at the bottom of the Eiffel Tower and the top of the Eiffel Tower. So I'm going to talk a little bit about the energy associated with these invisible particles, some things about how big they are, their mass, and their charge. Perhaps you've heard of atoms. Atoms are made out of basically three pieces. In the middle is a positive charged thing, it's called a proton. In the middle is a negatively charged thing, it's called a neutron. In fact, it wasn't until about the 1930s that we really figured out about neutrons, which is kind of amazing to me. And then around the outside are electrons, and those were the invisible particles that I wiped off my hair. They're on the outside, so they're easy to grab, and put on the comb and put on the electroscope. So those are big things generally compared to cosmic rays, because cosmic rays are subatomic particles. They're called high energy particles. They're from inside of atoms. They move at nearly the speed of light, and they start from stars, whether it's our sun, the star, or it's other stars in our galaxy, or it's stars in other galaxies. That's where they come from, spewing out from stars. And when they get to the Earth, most of them don't get to the Earth, if you think about the whole universe. Those that do get to the Earth run into atoms and molecules in the atmosphere, like oxygen, like nitrogen, and stuff breaks apart, and we get these showers. This is a drawing, this is not actually a picture, but you can really get the sense of a shower that stuff is flying out. One thing comes in, this cosmic ray hits something in the atmosphere, and you get a lot of little particles showering down on the Earth. I brought a Geiger counter, and every chirp, every random chirp there is some kind of a particle that's going through the detector there. And it's random. So you get long silences, and then more, and then 2, 3, and then random. Geiger counters were developed to detect cosmic rays. If you have some kind of radioactive material, we can, everything works so well. We can, oh, now it's better. We can get more invisible charged particles going into the Geiger counter. Some of you might be wondering, so Geiger counters, you've probably seen these from like the 50s. This is more modern looking, but maybe you've used radon detectors in basements or other places, same kind of thing. But you might be wondering, well, is any of this stuff dangerous? We just got a bunch of clicks, even without my radioactive samples. Is any of this stuff dangerous? Well, it depends on what you think dangerous is. For example, down here at the bottom, you don't need to worry about what a millisievert is, but a dental x-ray is down here at 0.01 worth of radiation, dental x-ray. The next thing on the list is a chest x-ray, which is about 20 times as dangerous, as much radiation as a dental x-ray. Up here at about 2 or 3 is about what people get a year. So you could do a little division and see how many dental x-rays you'd need to,
No more than 10.
yeah. So, and everybody gets this. Unless, of course, you're like at higher altitudes. And then kind of, instead of 13%, about 30%. Sorry. But higher altitudes, yes, you beat me in Denver, but Denver beats Los Angeles. So we get more. Now, if you want to go to higher altitudes, then we're talking about airline crews. And so it's maybe 3 times more than normal background. Most people don't think of being on an airline crew as dangerous, at least from a radiation perspective. CT scans, maybe some of you have had that, we're getting up there. Here at 100, background is here in the 2, 3, or 5. 100 is when we can start documenting that there's some cancer deaths. Unfortunately, with radiation, whether it's cosmic radiation or any other kind of radiation, we know when it's too much, but we don't know when it's safe. So, you know, up here at 1,000 or 5,000, we know that's too much. People die there. So we are down here. I think it's safe. What makes cosmic radiation or any of those other radiations dangerous is they're called ionizing radiation, because what they can do is they can knock electrons out. And I mean, I wiped them off my hair, it's not that big a deal. But if that happens in DNA, then we got a problem, because DNA replicates, and so if we damage the DNA, then we're making damaged replications. So that's what makes ionizing radiation dangerous. Good news is regular light, radio, TV, microwaves, no big danger there. Also, it turns out that alpha particles you can stop with a piece of paper. That's good, you want to protect yourself. Beta particles, which are like electrons, have trouble going through skin. X-rays don't have trouble going through skin. We have gamma rays and neutrons, and we're now talking about concrete. So you just check the lead-lined portions of the Victoria's Secret catalog, and you will be safe. But these things are, we clicked them here on the table, they are everywhere. And so if one of those cosmic rays goes through a computer chip, well, it can alter the workings of the computer chip. I talked about biologic samples, but they hit anything. So they can, here's one cosmic ray induced error for every 256 megabytes. So yes, your computer's at risk, but it's tiny. So you can't always blame cosmic rays on what's going wrong with your computer. We have some evidence that the Voyager satellite that went out past Jupiter and Saturn it malfunctioned in some way, and it could well have been from a cosmic ray. I am a lot more worried than NASA seems to be about astronauts because they are outside our atmosphere. Those cosmic rays are hitting them. They are more like they are a good target. And particularly if we're going to Mars or outer planets, they're out there for certainly months, maybe years, traveling through this kind of radiation. So early on, they took these kinds of electroscopes up in balloons, and they could detect not only from the bottom to the top of the Eiffel Tower, but as you go higher and higher and higher in the atmosphere, they would get more and more and more cosmic radiation. A good question would have been, when this thing was clicking, how did I know there was cosmic radiation versus terrestrial radiation? Well, it's just clicks. But as we go higher and higher in the atmosphere, we get more and more. We know that there's some stuff that's coming from outer space. It's not all coming from down below. And as we go higher and higher in the atmosphere, if we get more and more of this, that's saying that the cosmic radiation is being affected by the amount of atmosphere, the number of atoms that are between us and outer space. So it was a big deal. Balloons all over the place. We're taking stuff up. You take people up. You take these electroscopes up. And so this was, this quote talks about enters from above our atmosphere. But it's an interesting question, because we just got clicks. Which direction did it come from? So going higher, we detected more radiation. Robert Millikan in the 20s came up with this cosmic ray name. he looked for cosmic rays all over the place. Looked at high altitudes, looked underwater, they were everywhere. Which, maybe we should worry. In 1929, he discovered charged cosmic ray particles could go through 4 centimeters of gold. 4 centimeters is about like two fingers, which seems like a lot of gold to me, even if we just had to cover my little Geiger counter thing there. I don't know what Doge would think about that. But what we're finding is that these charged particles could go through gold, could go through aluminum, could go through lead, could go through lots of kinds of materials. And the way we figure out about the energy of these particles is a lot like figuring out if a material is bulletproof. So you set up the material, you start shooting bullets at it. If the bullets don't go through, it's bulletproof. If they do go through, not bulletproof. So we're calibrating the particles just like we would with bullets. If it goes through, well, then it has this much energy. So that's exactly what we do with these cosmic rays to figure out their energy. We just see, does it get through 4 centimeters of gold? Does it get through aluminum? Does it get through lead? Does it get through more lead? Does it get through... so that's how we figure out about the energies associated with these. Another nice feature about charged particles is that they can be directed with a magnet. As long as they're moving, you can direct them with a magnet. Earth comes with a magnet. So this picture represents Earth. Here's the big sun spewing out charged particles, and these charged particles can be directed by the Earth's magnetic field. So there's a lot more charged particles that could get to us, but because we have a magnetic field, we are protected. So those poor astronauts or characters going to other planets don't have that with them, so they get even more cosmic radiation. The aurora, because of the Earth's magnetic field, these charged particles are attracted more toward the North and South Pole and run into oxygen atoms, nitrogen atoms, and we get aurora. That's some visible piece of, you're not looking at cosmic rays, you're looking at cosmic rays hitting oxygen and nitrogen, and you get off some of these colors, kind of like neon lamps. It's that same kind of thing. And you get them at the poles because the magnetic field has bent the charged particles there. We don't get, just around here, we don't get aurora because the charged particles, we don't get enough of them. You may be worried by the clicks, but there's more of them because of the magnetic fields directing them at those places. So, in case you've gotten lost, this is what I've been talking about. So somewhere with stars, we create some charged particles that are spewing out, and they go past outer space and maybe run into satellites. But more importantly, they run into the atmosphere, and we're breaking atoms apart. And so we go from the primaries to the secondaries, the shower, and that's why these airplanes up there, they're closer, they get more radiation than we do here on the Earth. Most of the cosmic rays, the primary cosmic rays are protons, those charged particles in the middle of atoms. It's just the protons coming out. A few of them are electrons, some are helium, and some are heavier kinds of things that are arriving at the atmosphere. Then we get the shower. This is your opportunity to learn Greek. So, up here comes in maybe one of those protons, maybe an electron, maybe an alpha particle, maybe something else, runs into something in the atmosphere, and we get subatomic particles, stuff that was hiding inside of protons, neutrons, electrons, and we get this spray of stuff coming out. And they carry names like, so the symbol pi, so those are pions. And you can have positive ones or neutral ones or negative ones. You can get these E for electrons. Here's another pion. These go with muons. No, I'm sorry, that's a pion. There's a muon. There's another muon. So we get this shower of other subatomic particles that mostly go with Greek letters. Oh, this is an interesting fact. Let's see. It turns out that pions, these guys up here, quickly decay into muons. So these, the pions decay all by themselves into something else, muons. If you're curious and you want to comment about someone's brain, about 1 muon every second passes through your head. So when somebody says something silly, well, you say, oh, that was the muon that did so. All right. We're still using muons. We're still detecting muons. It wasn't so long ago, I think, they found in one of the pyramids in Egypt that there was a secret hidden chamber that they didn't know about. Muons are coming in from outer space all the time. They just set up a detector here and looked at the muons that were coming in this direction and then moved the detector to another place, and they could see triangularly in this area more muons got through than in places where the pyramid was completely solid. So, take your Geiger counter and go to Egypt. I'm going to talk about Mount Evans. It's now called Mount Blue Sky, but all of the time frame that I'm talking about is when it was called Mount Evans. So that's my, why I picked this. This was from Popular Science. We still have Popular Science now. 1936. Few riddles have roused greater scientific curiosity than these. Believed to originate in the empty space of the sky, the dark areas between galaxies, cosmic rays are the largest packets of energy known. They can penetrate lead 1,000 times as far as X-rays. What wonderful prose. Popular Science, 1936. A couple fact checks. Cosmic rays don't start between the stars. They come from the stars, whether, sun, stars. And the largest packages of energy known. Those of you who read food labels would know that there's more energy in a gram of chocolate chip cookie than there is in a gram of TNT. There's more energy in a gram of chocolate chip cookie than there is in a gram of TNT. Makes you wonder, what does the Pentagon do? Why don't they just drop chocolate chip cookies all over? Everything. This is like building world peace and all at once. So there's clearly more going on than just energy. It depends on how quickly you can get that energy out. That's why we drop TNT. We get a lot of energy out in a short amount of time, as opposed to a chocolate chip cookie, which eventually we get that energy. So there's that piece. cosmic rays, or the shower from cosmic rays, are tiny little particles. Yes, they're moving very fast. So yes, they have a lot of energy, but it's a little space there. So when they say it's the largest package of energy known, okay, in that little space, there's a lot of energy. Being hit by a ping pong ball versus a bowling ball, you kind of get that idea. So it depends how much energy in how big a space. But it was beautiful prose. I love that description. The Mount Evans lab started out with some experiments in tents at Summit Lake. The road to Mount Evans was built by the CCC, so it was a primitive road, and you could get to Summit Lake and you could set up things there. It is a little more protected if you're a scientist. And it's high up so that you can start doing some measurements. And the kind of measurements they did was with these kind of counters, and you see how many you get. And then you put a layer of lead and you see how many you get. And you put a layer of aluminum and you see how many. And so you can get a notion of the energy associated with the particles. And they start out in tents. And then in 35, they built these two A-frames. Those buildings were funded by John Evans, relative of Evans, of Mount Evans and Sand Creek Massacre and all of that. He was a trustee at University of Denver. These were prefab things, and you could well imagine that that was the case. Just looking at them, and they were delivered up there on a truck in 1935. I don't know what that really looked like, but then they just stuck them together. Nobody knew quite what the lightning and whatever was going to do. So originally they were copper clad. All of that's now covered. They copper clad them to like lightning rod to disperse the electric charges. So you can kind of figure out why they would do this in the mountains, and they wanted to be up as high as they could because they wanted to measure not so much the effect of the atmosphere, but, well, yes, less atmosphere, but you get more radiation when you're up there, and so you can measure the energies with different kind of shielding. So now we have a place where we can easily cart up lead, aluminum, graphite, paraffin, other kinds of things. We couldn't do that in balloons. So now we can do more experiments, bigger experiments, easier. All of what I just talked about was from the 30s and into the early 40s, and then came the war, and after the war, the interest in atomic energy grew immensely, okay? So anything that had to do with high energy particles was of interest. So in the late 40s, so after the war, high energy physics was a thing to study. And there was the Inter-University High Altitude Laboratory in Cornell and MIT and New York and Princeton and Chicago and the University of Denver were the founders of this laboratory that took advantage of the A-frames up on top of Mount Evans. Those of you who like to follow cost of living, so University of Denver, the primary benefactor, supplied $4,000. The other lesser institutions contributed $1,000. And over time, some of the partners changed, so we got University of Colorado and Syracuse, but you kind of see, all right, maybe we had $10,000 to run this laboratory. I don't know what Doge would say about that, by the way. Here were the lab administrators. Byron Cohn, University of Denver, he was chairman of the board, and my father was the lab coordinator. They were wonderful administrators and an acceptable father, but also they were cosmic ray researchers. So that's my ultimate connection with all of this. Science magazine still exists. It's put out by the AAAS, the American Academy for the Advancement of Science. It does all of sciences, biology, chemistry, earth science, all of these. So to get on the cover of Science magazine is a big deal. This was the research publication in the sciences. You were not a scientist unless you belonged to AAAS. And of course you would get this and go, that looks desolate, that looks wonderful, what a good place to do cosmic ray research. But to be on the cover of Science magazine is a big deal. You can see the A-frames. There are two parts of them. They're similar. So this is what it's like inside. So one half is the living quarters, so you can see the beds that fold down from, I don't know, the wall, the ceiling, what is it on an airframe? Anyway, the diagonal folds down, and so we'd have, this is the sleeping quarters, the kitchen was back there, dining area, working area. So one half was for the scientist to live there, and the other half was the experiments. These are Geiger counters, kind of like this little electronic one, but this is a small-ish one. The wires that are sticking out here are connected to a high voltage source. So you have high voltage at both ends, and when a cosmic ray or some particle goes through, it ionizes, it removes that electron, and suddenly we have a pathway between those two poles, and you get like a spark, but what you did is a click, a count. Oh, there was one. Oh, there's another one. And you're curious, well, does it make a difference? Are they coming straight down? Are they coming at an angle? Could they be coming horizontally? And so we see some of these set up horizontally. And yes, there is a difference. They do come vertically, they do come horizontally because of the magnetic field. They're bent in lots of different ways. And so we're curious, are they more energetic this way, that way? So you can see some of the Geiger counters there. And there's not enough room in the laboratory. So you have other trailers with equipment. This was the generator house. To get high voltage, you need a lot of electricity. And unlike now where you can take a battery pack easily, you needed a big diesel generator to run the equipment that they had at that time. The lab on top of Mount Evans was started there in the 30s and early 40s. In the late 40s, they built another laboratory at Echo Lake. It's not as high up, but it's another location. You can measure cosmic rays at Summit Lake, on top, Echo Lake, other places. So you can see some of the equipment, and then here's the lab when it's fully constructed. Over time, they built a dormitory, and all of these buildings still exist. They're near the campground or picnic ground at Echo Lake. So there's a dormitory, there's a lab down there, there's another lab up here. That's my reminder that I need to finish sometime. All right.
No, keep going, keep going.
No, you don't.
And laboratories, these laboratories look like big barns, because you bring in all of your equipment and you do your experiments, and then you take your equipment all back out again. I tried to emphasize that being in science or on the cover of Science magazine is a big deal. In 1948, if you were in Life magazine, that is a big deal. Scientists knew about science. Everybody knew about Life magazine. You would go into people's homes and they would have Life magazine there on the coffee table. And yes, Mount Evans Lab was part of Life magazine. And if you want to see more, it's over there, and you can take a look. But now, trying to make the point about big, it turns out that now high energy physics is bigger still. This is CERN, or the Large Hadron Collider. We're talking about a big circular track in France and Switzerland. So it's gotten bigger. It seems weird that to find these small invisible particles, you gotta have big things. So here are some more Geiger counters, and what they might do is make a layer of these and then have some shielding material and then have another layer of Geiger counters so you can see, oh, these came in, they didn't make it through the lid, so we can see, get some notion about the energies associated with these. This is a detector in CERN. You know, it's nice to have a big box, but like there are people. So yes, to find the smallest things, you need the biggest kind of pieces of equipment. In the 40s, this is what science looked like. So I'll show a picture of what might be going on here, but somebody's carefully measuring a photograph from some cloud chamber, some detector here, T-square. These are, so this is a visual. The Geiger counter tells you that something went through. This is more of a visual with a cloud chamber. So you get a pathway. So rather than have a discharge, what you have is a series of bubbles that follow the track. So here's a proton, here's some electrons, muons, some other. So this is what it would look like if you could see them as they move around. So each of those Geiger-Müller tubes are connected to a counter here, and so you can say which layer they might have come through. In the 40s and 50s, it was a family affair. So, especially during the summer when you could use the lab, scientists would come, bring their family, and we'll have morning coffee, and there's all the equipment in the background. It was truly a family affair, which is why I know so much about this kind of stuff. And it captured the popular press. So Life magazine here is from something that used to be called the Rocky Mountain News, but scientists trapped cosmic rays on Mount Evans. Here from the Christian Advocate magazine. I don't know what the competition to the Christian Advocate magazine was, but they had Mountaintop Laboratory and showing, these are balloon launches from the University of Denver. Here's filling the balloons, but here's top of Mount Evans. Again, nuclear or atomic kinds of things really did capture people's imagination following the war into the early 50s. This was the announcement that went with me being here. So this was also from the Rocky Mountain News. Discovery discussed at Idaho Springs Parlay, carefully located here above the Harmon Fabrics and the false teeth ad. We have a parlay in Idaho Springs. And it was a big deal. So registration was at the Idaho Springs High School. You could call them up there at Idaho Springs 91. And that's what the high school looked like at that time. So that's where registration was. So we had people from all over the world, mostly the United States, coming to Idaho Springs for this conference. And they came to Idaho Springs because it was close to the laboratories where the work was being done. Yes, lots of things have improved since the 1949, but if ladies did come, as wives of the scientist, I'm sorry, they got an excursion to a world premiere showing of a motion picture. But that just adds to the emphasis that this was a big deal. Because it was going to be a world premiere. All right, so there were lots of sessions led by important scientists. Anderson discovered that there's such a thing that looks like an electron but has a positive charge. He got a Nobel Prize for that. He was leading a discussion about spontaneous disintegrations. It turns out that some of these particles, all by themselves, will decay, disintegrate. Lifetimes. So if they're going to spontaneously disintegrate, well, they have a lifetime, how long they might last. And we were really interested in a lot of disintegration because that's some of the shower business. Rossi never got a Nobel Prize, but it was quite famous in high energy work. And looking at, he did a lot with the Manhattan Project. So he was interested in nuclear interactions and cross sections of interactions. But he was another discussion. These are pictures from the Echo Lake Lodge. So here's everybody on the porch for the group photo, and inside they'd have meetings that looked like this. And maybe some of you have eaten this is like in the dining room, you may have eaten there. They shoveled the tables out and left the chairs. Because just down, across the parking lot and into the campground is the Echo Lake Lab. And we could take field trips up to Mount Evans. They had some high-powered physicists as some of their keynotes. Archibald Wheeler was one of the founding fathers of cosmic ray research, so he's talked about cosmic and terrestrial fields. These are like magnetic fields on cosmic rays. And Marcel Schein talked about the composition of some of this radiation. Of course, every conference has to have a banquet. We'll just bus everybody over that Lariat Trail over to Teller House in Central City. And Robert Millikan, that I talked about at the beginning, that named cosmic rays, was going to talk about early investigations there at the Teller House. I talked earlier about wonderful prose. Here's another set of wonderful prose. The subject of cosmic rays is unique in modern physics for the minuteness of the phenomenon, the tiny nature of this stuff, the delicacy of the observations. You may think these Geiger counters look kind of clunky, but we're trying to capture little tiny things. The adventurous excursions of the observers. Welcome to Idaho Springs, Mount Evans. The subtlety of the analysis and the grandeur of the inferences, because all of this work that started here is now the precursor to what you have with the Large Hadron Collider. The plaque that was mentioned that is just outside Echo Lake Lodge talks about some people and specifically references a muon decay experiment. that is proof of relativity. I will, if we had a bunch of automobiles, and the fastest that they could go is 100 miles an hour. That's the fastest. That would mean, you got this line up with them, you could go 100 miles away, and in an hour, they would get to you. If they go 100 miles an hour, that's the fastest that they go. If you got someone who's a little slower, then maybe they only go 90 miles or 50 miles or something else. But if they go as fast as they can, in an hour, they'll get 100 miles. So if you are 100 miles and 10 feet, you are safe. You are not going to get run over. What they found with muons, there is a fastest speed that things can go. It's called the speed of light. That's the fastest speed that things can go. So that if you know that a muon only lasts this long, well, you could do that same experiment. And so if you go at 100 miles an hour, you're going to be here. But what they found was the equivalent of automobiles that have gone 120 miles, 130 miles. The fastest that they could go is 100 miles an hour. So in an hour, you'd think they go 100 miles. But we found that they went further. In this case, it's muons instead of automobiles. But we found they went further. They didn't go faster. You could only go like 100 miles an hour. The reason they could go farther is because time is different if you're moving. So while us out here are looking at our clock for an hour, we know where you are. For the muon, for the car that's traveling, time is different. In fact, it's slower compared to our time. So that compared to us, they have more time to travel 100 miles an hour. So they go more than 100 miles. So that's the kind of thing that they found with muons. They expected them like to all decay by the time they get here, but we find them down here. So that we have some proof that for the moving object, time is different, which is a big deal, which is kind of amazing to do with invisible particles. And we know that they last longer than we thought they did. So something like that is probably worth a plaque. And so the American Physical Society has identified historic sites all across the nation, and Echo Lake is one of those. There he is. Echo Lake is one of those, and this was from the dedication there. So you can, just back up there was where all those scientists were sitting. So it's interesting to see questions that were asked and the mysteries that were investigated, and a little bit about some of those investigators. So, thank you. Well, I made it under an hour. But I'm happy to try and do questions. I've also got some stuff here, and if somebody turns on the light, it'll be easier to look at the stuff, but I can do a couple questions.